Hello, my name is Bogdan Grechuk, and I want to present a paper, our joint paper, about Diophantine equations with three monomials. So, Diophantine equations is polynomial equations in this form, where we are looking for integer solutions. By famous Mathiasevich theorem, which was a solution to Hilbert 10 problems, there is no general algorithm to solve all equations. Therefore, we need to consider restricted classes of equations. For example, we may restrict number of variables. For example, if we have just one variable, we have equation one variable, it's very easy to list all integer solutions to this equation. However, already for two variables, it's a major open question how to find all integer solutions. Another restricted family is restricted number of monomials. For two monomial equations, so this equation in this form, it is well known that there is a general algorithm for solving all equations of this type. But for three monomial equations, it's open in general. For example, a special case x to the power n plus y to the power n is equal to z to the power n is a three monomial equation and is a subject of Fermat's theorem, famous result. Yeah. So in the number of variables, the first open case is two variables. For monomials, the first open case is three monomials. So it's natural to have a look at the case of two variables and three monomials. In this case, the equation has this form, and after cancelling common factors, it reduces to this form: ax to the power n plus bx k y to the power l equals cy to the power n. Our first main theorem in this paper is that there exists a general algorithm to solve all equations of this type. Main idea of the proof: so if a is any integers, let's denote AP the largest exponent such that p to this exponent is a factor of a. Yeah? So AP is the exponent with which p enters the prime factorization of a. So then for any three numbers a plus b plus c equals 0, the two smallest out of exponents AP, BP, and CP for any primes should be equal. So that's a very easy but very useful result. Because if we apply this result to our equation, we get that for any p which is not a factor of a, b, c, the exponent is enters the first monomial is this one, the exponent p enters the second monomial is this one, and the exponent p equals the third monomial in this one. So three exponents must be equal, and from this we can easily solve these equations and have some relations to exponent, and this allows us to reduce this equation to equation of the simple form a y to the power m equals bx to the power n plus c, and this type of equation is known to be solvable by Baker's theorem. This allows us to prove the general algorithm for all two variable three monomial equations. The same idea works for some special general three monomial equations with no restriction for number of variables. So this idea allows to reduce this equation to equation with independent monomials, which means that monomials do not share variable, and this new equation is sometimes easier. For example, equation of this form, x to the power a, y to the power b plus all permutation, yeah, like this. We apply this method and reduce to equation to this equation. And this equation we know how to solve by Fermat's theorem. Okay? So this allows us to solve original equation as well. Also, we prove for the general three monomial equation like this, yeah? You see there are some exponents alpha I, beta I, and gamma I. So if the corresponding system of equations has non-negative solution in non-negative integer, then we prove that our method always works, and we can solve all such equations. And we checked how many random equations satisfy this condition. For example, we fix number of variable n, we fix degree d, and then select all exponents at random on the interval 0d. Then, for example, for 3 variables and degree 10, only 30% of equations are solvable by this method. But if we have 10 variables, then already 99 equations are solvable by this method. If we have degree 10 to the power 5, then for 3 variables, only 20 equations solvable by this method. But for 10 variables, already 98% of equations solvable by this method. So in general, empirically, we will see that if we fix degree and number of variables goes to infinity, then the percentage goes to 100%. So empirically, it looks like for our method is able to solve 100% of all three monomial equations as the number of variables goes to infinity.